Okay, say I asked you to imagine two things that are opposites. Your mind might go to hot and cold, chocolate and Brussels sprouts, or even order and chaos. But actually, these last two aren't opposites at all. In order to understand what I mean here, first we need to understand deterministic systems. These are systems where information about the present states will help us predict their future states. Now, this sounds like the antithesis of chaos, but actually, all chaotic systems are deterministic systems. This is the basic idea of chaos theory, that there's an underlying pattern and organization to chaotic systems, even though they seem unpredictable. So, if chaotic systems are predictable, what makes them so hard to predict? Why are weather forecasts wrong so often, and why does the stock market rise and plummet without warning? The answer is sensitive dependency on initial conditions. This property of chaotic systems, also known as the butterfly effect, means that tiny changes in one state of a system can cause disproportionately large effects in later states. So, to make accurate predictions about chaotic systems, we would need measurements down to infinite decimal places, because any differences between the real conditions and our measurements would be magnified over time. To imagine this, let's say you're trying to get to point C, and you call a friend for directions. You tell them that you're currently at point B, and so they tell you to walk 2 blocks left and 3 blocks up until you arrive at point C. However, you're actually 1 block left from point B, at point A. So when you walk 2 blocks left and 3 blocks up, you're not at point C, but 1 block away from it. As you continue walking, the difference between you and point C keeps getting bigger, as the initial difference in position is multiplied. Now imagine this with enormous systems, like the weather, and it's clear how our predictions can get distorted. In addition to their sensitivity to initial conditions, chaotic systems have one other property: a strange attractor. An attractor is just a series of numerical values that systems trend towards as their evolving variable changes. These values can be plotted in 2 or 3 dimensions, like a shape or a fractal. A fractal is an infinite pattern, which looks the same no matter how much you zoom in. When attractors have a fractal structure, they're known as a strange attractor, and this is one of the defining characteristics of a chaotic system. So, chaos is more predictable than it seems. What's the big deal? Why is this even important? Well, chaos theory shows us the limitations for making predictions, and also helps us to better understand chaotic systems. Chaos theory currently has applications in biology, cryptography, and robotics, and in the future, it's possible we could use it to predict traffic conditions ahead of time. Chaos theory opens up the possibility of predicting more about our world, and it shows us that even in the most chaotic places, order remains.